Okay, we're going to carry on talking about Le Chatelier's principle, which is this thing over here. Right, what he said was, whatever change is imposed on a reaction at equilibrium, the position of equilibrium will move so as to oppose the change. Okay, so we looked at heat, the effect of temperature. If you increase the temperature, the reaction will try and decrease it. What's the only way it can decrease it is by moving in the endothermic direction, and vice versa. If you drop the temperature, it will try and warm it up by moving in the exothermic direction. So now we want to have a think. After we've done temperature, so we'll think about pressure. Okay, pressure. Now, what is all of these reactions are all involve just gases. Okay, what is pressure? Well, pressure, if you have a container, you've got gas molecules flying around in it, and they are banging into the sides. Okay, and it is, well, it was the change of momentum of those particles, which is puts a force on the container, and force divided by area is pressure. Right. So the important thing to take home from that is that the more gas particles there are, the higher the pressure will be. Okay, so right, let's see what would happen if we allowed ammonia and hydrogen to reach equilibrium with ammonia there. Okay, form ammonia. So what would happen is, right, let's think. If we increase the pressure, I'll write a little thing there. We increase pressure. Right, on the left-hand side, we have got one molecule of nitrogen and 3 molecules of nitrogen. There's 4 gas molecules. If it all reacts, you'd only end up with 2 molecules there, 2 molecules of ammonia. So if we increase the pressure, it will try and decrease it. How can it do that? By moving in this direction, because there's fewer gas molecules. So the equilibrium moves to the right. The equilibrium moves to the right. Okay, let's look at the next one. We've got the nitrogen oxide example. We've got 2 molecules of gas on the left, and we've got 1 on the right. So if we increase the pressure there, the equilibrium will also move to the right. So equilibrium moves to the right there, equilibrium moves to the right with that one. The next one, the methane one. Okay, so we've got water as a gas there, high temperature steam. So you've got 2 molecules on the left-hand side, and you have got 4 molecules on the right-hand side. So this one, if you increase the pressure, it will try and decrease it by moving backwards. So this one, the equilibrium will move to the left. And then the final one, well, we've got hydrogen and iodine. So we've got 2 molecules on this side, and they are going to react to form 2 molecules of hydrogen iodide. So you've got the same number of moles of gas on the left and the right. So the increasing the pressure there will have no effect on the position of equilibrium. Okay, so you just look, if you increase the pressure, you look for the fewest number of gas moles, and that's where the equilibrium is going to move. So anyway, let's have a little think about the ammonia reaction. I'll just write it down again. And that reaction is actually slightly exothermic in the forward direction. So delta H is negative in the forward direction, it's exothermic. And if I draw my little that we had in the last video, so here what I'm going to have is, this is the percentage converted, the percentage of the nitrogen and hydrogen converted to ammonia, and this is time. Okay, so we do it once and we get a graph like that. Okay, that would be 100% up there, and you never get, this line will never reach 100%. It looks like it stops, doesn't it, about there. It looks like it reaches equilibrium about there, because we said before the forward reaction is equal to the rate of the backward reaction at that point. Now let's see if we did it at a higher temperature. I think we mentioned it before. You would get a line something like that. Now why? So this is at higher temperature. There's two things to note here. One is to do with equilibrium, and that shows you that the equilibrium position is it's to the left. In other words, you get less ammonia at higher temperature. Well, why is that? Because the forward direction is exothermic. So if you come along and increase the temperature, it will try and decrease it by moving in the end direction. The other thing to notice with this line here is it's steeper there. Okay, why is it steeper? Well, it's nothing to do with equilibrium, it's to do with rate of reaction. Because the temperature is higher, it's going to react faster, so it will reach its equilibrium position faster. So this features equilibrium, at this about there, yeah. Whereas the other one, it took a lot longer. Okay, so we just get rid of those bits and get too messy otherwise. Now let's think about if we do a higher not a higher temperature, let's do a higher pressure. Now, let's think, how will that do? We've said, right, we've got 4 gas molecules on the left and 2 on the right. So higher pressure, you're going to get the equilibrium position will be more ammonia. So it's going to be up here. And also, can you think what would happen to the steepness? Well, if you've got higher pressure, the gas molecules are all closer together, so they're more likely to collide. So the rate would be a bit higher. So you would get a line which looked, well, it's got to be steeper than the black line. So it'd be something like that. So steeper, and you get a higher yield of ammonia. Let's do what would happen if you did it with a catalyst. Now catalysts speed up the rate of reaction, but they don't change the position of equilibrium, because they're going to increase the rate of the forward and the backward reactions equally. So if you did it with a catalyst, it would be steeper, but it would be leveling out at exactly the same point. Sorry. So that's with the catalyst, that yellow one there. The position of the equilibrium isn't altered. Okay, so that's just a nice little graph to think about things. I think we should also say here, it's a bit of a GCSE, I think, but if you remember the conditions to make ammonia, okay? So to make ammonia, the Haber process, you would, for a good equilibrium yield, you wanted to push it to the right, good equilibrium yield, you should use a low temperature. But you can't use the temperature too low, because if you do, the reaction is so slow, it will take an awfully long time to reach equilibrium. So I'll say that's a low temperature. It takes a long time to reach equilibrium. So that means I think the Haber process is done usually at 350 degrees C, which is a pretty high temperature. Room temperature is, room temperature is 20 degrees C. They could do it 20 degrees C, save all themselves the money of the energy cost, get a much better yield. Why don't they do it 20 degrees C? And so rate of reaction would be so slow it would take forever. So 350 is a compromised temperature. You probably remember that idea. Another thing would be what kind of pressure to make ammonia. Well, you should use a very high pressure, shouldn't you? Yeah. But there's a limit to how high the pressure that is practical to use, because yes, you do get a better yield of ammonia, but you have to make all the containers much stronger to withstand those pressures, and there's a cost involved in that. So it becomes a point where it's not economic to increase the pressure anymore, even though you do get a better yield. Finally, just to finish, you'll see in a lot of books this word, this little phrase here called a closed system. So if you get any definition of Chatellier's principle, it will all say in a closed system. You don't need to write that down in an exam, but it wouldn't probably always say that. And just to explain what a closed system is, let's think about if I got some magnesium and I put in hydrochloric acid. HCl. What would happen is it would fizz up and it would make magnesium chloride solution and aqueous hydrogen gas. Now we'd normally do that in a beaker. There's a beaker with your bit of magnesium ribbon in it, and it would carry on fizzing until it all the magnesium had gone. Right, this beaker's open, so what's happening to all the hydrogen? The hydrogen is escaping. It doesn't stay there, so we say this is an open system. If you did this reaction in a closed, if you did it you've got a Coke bottle and you can do this, put it in there, you put your magnesium in there, and you screw the lid on it. So the lid is on. This is now called a closed system. Well, the reaction appears to stop. Right, because it reaches equilibrium. We never think of this being an equilibrium reaction, because we always do it in an open system, in a beaker or a test tube or something. But if you turn it into a closed system, it will stop and it will reach equilibrium. Let's think what's happening in this open system. Right, all the H2 you make escapes. What does Le Chatelier tell us? If you keep removing one of the products, if you remove it, what's it going to try and do? It tries to make more product. And then that comes along and that escapes, so it tries to make more. So the reaction just keeps going further and further forward until it goes to completion. If you put a lid on there, what you do is you stop that product escaping, and so you get a reverse, the reaction can go backwards and forwards, and it will reach equilibrium, and you'll get to a point where there's a bit of magnesium in the acid and it doesn't dissolve. You do the experiment correctly, even though there's enough acid to react with it. So that is just the difference. They're just explaining what a closed system is. It's nothing terribly fancy. It's just that you put a lid on it and keep all the reactants in there. And of course, we don't normally use closed systems when we're doing reactions in the lab. We let it all, gases escape.